All right. I'm going to set the share screen. Okay, so I can go ahead and get started for the lecture number 10. So this is the last one, but I guess you probably have more questions here. So the logistic regression, the goal for doing that is to evaluate association between a binary outcome and the independent variable called the predictor variable. So you can also think there is a main independent variable of interest we call the exposure variable with the outcome. So outcome here has to be a binary variable, and therefore this is used for looking to comparing the difference, how the difference in the independent variable can produce the difference in the odds ratio of the risk defined by the binary variable we call event variable or the disease variable. It's really the binary variable you can think of as either disease, no disease, or event, no events. And sometimes it can be like, say, if it's a disease, we can call this a risk. But sometimes this event may not be a disease, may be a good thing. Or like, say, if you want to see the patient recovery, and then if the indicator is recovery, this is going to be a good thing. We're not going to call this a risk. But only if the binary variable is a disease variable or mortality or something like that, we call that a risk. And again, the logistic model, the main goal or the main scientific question is to look at the relationship between the exposure and the binary outcome variable. And it could also be confounder variables, which related to both exposure and the outcome, but not in the causal pathway, which means it's not an intermediate variable between the relationship from the exposure to the outcome. And the outcome has to be a binary variable. Disease, no disease, event, no event, something like that. Exposure can be any type, can be a continuous, categorical, ordinal, or can be a count variable, but the interpretation of the results will be different based on the type of the exposure variable. And also confounder can be continuous, can be categorical, can be ordinal, or any type of variable you may see here. And here's the model. And the model is not, the thing that is different from, in terms of the model, the thing's different from the linear regression is you're not directly modeling or not directly look at the expectation of your outcome y. Instead, you're looking at a function of the outcome y. And here P, you can consider P is the expectation of your y, only if your y is a binary variable. Because if your y is a binary variable, expectation of your y is just the probability of the y equal to 1. So this only if you code your variable as 0 and 1. If you code as 1 and 2, it won't work. Only you code as 0 and 1, the expectation of your outcome y is equal to the probability y equal to 1. So you can easily get this. It's a simple statistical result because it's the event within a specific time period for cohort study, and we call this P. And you can see that what you model in logistic is a function of the expectation of your y. In the linear regression, you directly model the expectation of y because the expectation of y is on the left-hand side of the equal sign in all the linear regression models. But this is we call the generalized linear regression model. The reason we can call the generalized linear regression model is because on the left-hand side, it's still a function of expectation of y. It's not totally of the expectation of y. We still need to have the expectation of the outcome variable y, but this is a function. Only if we do a transformation, we will call it, put a function on expectation of y, you will have a linear combination. So that means you can use the linear terms or the additive model, which means adding the effects together to estimate the logit function of the expectation of y. And this logit function, it happened to be interpreted as the log of the a function of your expectation of your y. And if the expectation of your y is equal to p in the cohort study, this is interpreted as the disease prevalence, because the probability of an event within certain time period, you should be able to get a cumulative number of the disease cases. And the cumulative number of disease cases over the total size of the population can be used to approximate the disease prevalence. Although it's not the perfect disease prevalence definition, but it's similar to disease prevalence. And usually people can define that as disease prevalence. So this is to say the log function of the, a function of the risk or the function of disease prevalence is equal to a linear combination. And this logit function is happen to be the log of the odds. So if we interpret the p, the expectation of y as the risk of the disease, and the risk over 1 minus the risk is the same as the risk over the probability of do not have the disease, is defined as odds in statistics, both statistics and in epidemiology. So you can see the same definition. And therefore, we can easily interpret as a log of the odds function can be modeled as a linear combination of the predictor variables x. And here x1, you can always put x1 as the main exposure, and everything after x1, x2 to sk can be considered as the covariates or the confounding variables, which have the impact on the relationship between x1 and p and outcome. Actually, p is actually the function, the expectation of y. You should keep in mind, this p is not just p itself, it is a expectation of your outcome variable y. All right. And as I said, in the cohort study, this p can be interpreted as the disease prevalence. And in the case control study, this p is basically just the probability of the case, or we can consider it as a risk. Or in the cross-sectional study, because you only look at one time point, this p is basically just the probability of disease present. It won't give you the prevalence because you will not have a cumulative number of cases. Some people may explain as the, in the cross-section, explain this as the disease incidence, but it's not exactly the disease incidence, because this may be the case cumulated, or may not be the case which happened right at that time point. All right, and then after you do a simple math, you can see this p, what we call this risk of disease, is actually a function of the estimated parameter in the logistic regression model and the values of this random variable from x1 to sk. And here we call a logit function, is a log of the odds. And here we call this xpid function. You don't have to remember that name, but some people use the xpid. Xpid is the reverse of logit, which indicate this function. It's basically just a function of the exponential function of these linear combinations. All right, so here's the model setup. After you know the model setup, the other thing I want you to know is the relationship between the p and x. So based on this model setup, you can actually easily get a relationship. It's actually, we call this S shape, which means as the x increases, the probability does not increase linearly. It's actually have this kind of relationship, which means, like, say, at the two tails, or like very beginning at very end. It's just like the flat. It's like flat, like say at the end, flatten the curve, but at the beginning is increased very slowly. So only if in the middle it's increased dramatically, or like exponential. So it's exponential only if in the middle part, but eventually it will flatten the curve. The reason is to the cap. The cap of that is 100%, and lower we call the floor function is 0. Your ceiling is 1, because the probability is always from 0% to 100%. So the 100% is the same as 1.0. All right, so that's the logic function. So logic function is the same as the log of the odds. And then next thing I want you to know is how this estimated odds ratio from a logistical model related to the 2x2 table. So usually if you have a very simple design, you only have one exposure, and then you have disease status, you can easily summarize your data in this 2x2 table. So for example, the columns represent the exposure status, exposure versus no exposure, and the row indicate the disease status, disease versus no disease. So basically in each cell, A, B, C, and D is the number of observations in that situation. So for example, A is the number of study participants, or number of individuals have disease and exposed to that exposure variable. And B is the number of disease not exposed, etc. And your odds ratio is basically the odds, the ratio of the odds by the two exposure groups, because your main goal is to compare the odds for different exposure status. And this is why the exposure is of interest, is you want to see if only if the odds are different between the exposure status, we can see there's an exposure effect on the disease. Because if they're the same, that means the exposure will not have any impact, will not have any effect on the risk of disease. So it's basically the A over C is the odds of case in the exposure group. B over D is the odds of the exposure in the non-exposure group. So it's basically A over C over B over D, and they sum up to simplify to AD times BC. So AD is just the product of the diagonal of the 2x2 table, and C times D, C times B is the off diagonal. All right, so for the simple logistic regression, you only have one exposure variable, x1, and therefore the model is simplified to the log of the odds is modeled by a intercept beta 0 plus your beta 1, and you beta 1 have a different interpretation based on the type of the data. So if beta 1 is continuous, and then you estimate beta 1, B1 is a log of odds ratio for 1 unit difference in x1. So in the cohort or cross-sectional study, this exponential of the beta 1, because the B1 itself is a log of the odds ratio. So if you do exponential, it cancels the log. So this is going to be an odds ratio comparing two populations with 1 unit difference in exposure x1. And if x1 is binary, the B1 is the log of odds ratio comparing exposed group versus unexposed group. So which means the exponential of your B1 is the odds ratio between the exposure and non-exposure group. And that's interpretation of the beta 1, so that's the main effect. So beta 0 is most likely to be nuisance, because in most situations we're not interested in interpretation of beta 0 itself. But we can still do the interpretation, because interpretation is different from beta 1. So if x1 is the continuous variable, so exponential of B0 is the odds of being diseased at x1 equal to 0. So remember, beta 0 is not interpreted as the odds ratio, it's interpreted as the odds. And we call this baseline odds. the reason we call baseline odds is it's always at the odds for a continuous variable equal to 0, or if x1 is binary. So this is the odds of being disease or for the n-exposed group. So that's the interpretation for beta 0 in the simple linear regression. And in the multiple linear regression, you can see we have multiple predictor variables from x1 to xk. But again, if x1, we can still treat x1 as the main exposure and all the other variable as the covariates. And here the interpretation of the beta 1 term or the B1 term, the B1 will be the log of the odds ratio for one unit difference in x1, the main exposure, when all other covariates or factors are held constant. And if x1 is binary, and then B1 is the log of odds ratio comparing exposure group versus non-exposure group. And also when the other covariates or factor from x2 to sk are held constant. And similarly, the interpretation of this beta 0, B0 terms is the baseline odds. So baseline odds means we need the odds at all the predictor variables simultaneously equal to 0. So it's not only the exposure equal to 0, but all the other covariates equal to 0. Or at the reference level, depends on the type of these other variables. If these all other variables as the continuous, they need to be equal to 0. But if they are binary, you need to keep this as baseline because you use the reference group as a 0. And if this x1 is binary, and then exposure of beta 0, B0 is the odds of being disease for the n exposure group, when the other covariate equal to 0 and the factors as reference level. Okay, and here talk a little bit about the estimation, but you don't have to worry about the explanation. So this is a theoretical thing. I usually put this in the theoretical class. But you just need to remember the estimation for the logistic regression is different from the linear regression. In the linear regression, we usually use the least square method. So this is nothing related to the likelihood. But here, because it's not very easy, it's no way we can use the least square to do the estimation of the beta parameter because your data type is not continuous. It's just a 0 and 1. And there's almost no way you can calculate a meaningful variance for that. And minimize that variance. So the way to do that is you need to specifically write down the likelihood function. So likelihood is just the distribution of your outcome y. So if your outcome y only can take two status, 0 and 1, and this is the binomial distribution in statistics. So it's basically the whole likelihood depends on the binomial likelihood function, and we can replace the parameter in the likelihood function bi with the model parameters, because you see this bi is just the estimate of the estimated parameters beta 0 to beta 1 and the random variable from x1 to xk. And then we can basically replace this whole thing by the model parameters. And then we can, when we have the likelihood right down, we can do, again, the similar thing as the least square, which is to the partial derivative in terms of each parameter. And when we maximize the parameter means we put this derivative equal to 0 will corresponding to a maximum number of that likelihood. So that's basically just the idea there. And then, so this part you just need to know, and serious problem for the estimation we call over dispersion, which means the variance. The real variance is actually much greater than the variance, the theoretical variance based on the binomial distribution. So in that case, so you can have the remedies, which means you can use the beta binomial model, or you can use the quasi-likelihood inference. So the beta binomial is a different model, but the quasi-likelihood is you can still use the same model, but you're not using the maximum likelihood, use the quasi-likelihood. So this is a very advanced topic in statistics, so you don't have to worry about that. Or you have to use the Bayesian reference, which is not entirely based on the likelihood. So the hypothesis testing you have to know is here usually we test testing the effect of the exposure on the outcomes is equivalent on testing if the odds ratio equal to 1, versus not odds ratio not equal to 1. So the odds ratio equal to 1 is equivalent to that beta parameter is equal to 0, because the odds ratio is equal to the exponential of the beta parameter. So exponential of 0 is equal to 1. So they're equivalent. The other two things I want you to know is we already talked about the confounding and effect modification. It is how you can test confounding and effect modifications in logistic regression instead of in the linear regression. So, but this is the same thing. So in the linear regression, you know, if you test if a certain potential confounding variable is a real confounder, so you can do the parameter beta and compare if the beta change more than 10%. And you can use the 10% rule to specify or to conclude if this is a confounding variable. So this is a similar way in this logistic regression. But the things you can use is to compare odds ratio or log of the odds ratio. So log of the odds ratio is just the estimated parameter beta, and the odds ratio is just the exponential of the beta. So you can either compare the beta or odds ratio of the beta to see if you have more than 10% change with and without the confounding, potential confounding variable, so which can give you a conclusion on that. And effect modification is the same way. So if you have more than 2 predictor variables, and you can see if one predictor variable, if one factor is effect modifier on the relationship between the other predictive variable and the outcome, and then you can put the interaction terms between this factor variable with the exposure, and then you test the significance of the interaction terms. And there's a formal statistical test for the effect modification or interactions. So this is a similar way as we do for the linear regression. And my example here is basically, again, used to testing the effect modification and also the interpretation of that. So I'm not going to go over this because you can see my video for lecture number 10. And we don't have a data for this. This is just for demonstration to how to evaluate the effect modification. Is we specifically need to look at the interaction terms between one factor and the other factor. And we can evaluate them based on the p-values or the 95% confidence interval for that effect. And remember, this coefficient is the log of the odds ratio. It won't be able to interpret it as the log odds ratio. And in this specific SAS example, so I actually give more details there, like say what to interpret the SAS result, because this is all from SAS output. So this is the example using infectious disease, which is a dengue fever, but this is caused by a virus. So similar to, but this virus will use the vector is mosquito. And here, therefore, you have 2 different predictor variables, 3 different predictor variables. So actually age and the use of the mosquito netting and also the geographic location. And this is the categorical variable, have more than 2 categories. And this mosquito using is a binary variable, and age is continuous. And the infectious status, the dengue fever status, is actually at 0 and 1. But it originally coded as 1 and 2, but it's type of 0 and 1 data. Is a binary data we can use.
Can I ask you a question really quick?
Yeah.
Just on the dummy variables. So does it make a difference if they're coded 2 and 1 and 1 and 0, or do you treat them the same way? in terms of the model.
You mean for the outcome?
Yeah. Well, no, not for the outcome. More when it's an independent variable affecting the actual outcome.
You mean for the factor, or for the sector, or for the?
Yeah. So let's say, for example, let's say the mosquito net was 1 and 2.
Mm-hmm.
So instead of 0 and 1, would it affect the model?
It depends. So if you are talking about how to using SAS, right? So if you're using SAS, if your mosquito is 2, 1, and 2, not 0 and 1, you can specify the reference as 1 or 2.
Okay, but
adding one is reference. But in the result,
yeah,
if you do them reversely, the parameter estimator will have a different sign, right? Like say for mosquito using, if you use the other one as a reference, this is going to be negative 0.33 instead of 0.33. It will have a reverse because you put the 0 and 1 reverse, the beta parameter will be a reverse. But the interpretation will be the same. It won't hurt your interpretation.
Oh,
okay. It's interpretation because the interpretation for this will be interpretation different from the interpretation for the others because you're using different reference group. But it's actually the same thing, right? Because the negative interpretation, the odds ratio will be 1 over the other interpretation. It's the same thing. It won't hurt your final interpretation, but it might hurt it might impact the value of the estimate.
Okay, so for example, in the final model, you would plug in 1 if it included that specific variable, or you would eliminate that term and coefficient altogether if it was 0. So so you get what I'm saying?
You mean for factors? Well, it's different. Like say, if you have a binary variable, it's different from if you have a categorical variable more than 2 categories.
No. Let's say you have a binary variable. Let's say it's mosquito net, for example, but it's instead of 2 and 1, it would be 1 and 0. Or is that what it is right now? I don't remember.
But okay. 1 and 0, as I said, if you put 2 and 1, 1, 0, and now the reference is not going to be 0. The reference be 1.
Yeah.
It still do the same thing.
Okay, but in the final model, will it be different? Okay, so you always plug in 1 if it's corresponding to the dummy variable 1, and you put in 0 if it's corresponding to the reference group. But let's say the dummy variables are 2 and 1. Would you plug in 1 when it's the reference group rather than 0 when the dummy variable is 1 and 0?
And then it would depends on how you define the 1 and 2, right? Is 1 means using or 2 means using? It's different. In that situation, I would suggest you to first convert to 0 and 1. And 1 always means, like say, if this name is mosquito using, right? The 1 always means use it. 0 means don't use it.
Yeah.
Like say factor 1, if you put that dummy variable, and 1 always means you in sector 1, and 0 means you're outside sector 1. But you always, I mean, if you cannot do that, if you even think that's confusing, my suggestion is you always first convert to 0 and 1 variable.
No, that it's not confusing. It's just, for example, in the homework, this is in reference to the homework 5, with the problem where it includes the dummy variables 2 and 1 for gender, for male and female.
Mm-hmm.
And I was curious to, when you have to do the calculation by hand at the end, the second to last problem, do you plug in 2 if it's a female? Or do you plug in 1 if it's a female and 0 if it's a male? Or do you plug in 2 if it's a female?
So the way to do that, if you not treat this, SAS to do that is if you treat as a 0 and 1 variable, so you will use the rule. So if you don't treat this as a 0 and 1 variable, you treat it as 1 and 2. Mm-hmm. It will base on the characters. So the only it's like say if this variable is not a numerical variable, is a string variable, it always use the largest is first sort by alpha, right? So sort by alpha and the alphanumeric, and then they always use the last one as the reference group. So that's the way SAS doing it. But if you're saying that's not easy to do interpretation, or you think that's confusing, that's what I mean, because sometimes it's confusing. You always can first convert that to 0 and 1. So if you convert to 0 and 1, it's not going to be a string variable anymore. It becomes 0 and 1 variable, and then you can use the new variable as the predictor instead of the old one. So if you do not use 0 and 1, use other values, so SAS will always treat this as a string variable. And as I said, always sort by alpha. And then they always pick the last one as the reference. So that's the way SAS doing it.
No. So I'm just confused about whether you would plug in. Would you include a value reference 2 in the final model? Would you include, let's say the coefficient is 0.5? Would you do 0.5 times 2, or would you do 0.5 times 1 if we're using 2 and 1, and 2 is not and 1 is the reference variable? So 2 is
this is what I'm saying. So if you use 2 and 1, it's similar as you create a dummy variable to 0 and 1. Right?
Okay.
This is similar to sector, right? Because sector is similar to not 0 and 1. So the way to do that, so if you have 2 and 1 to do that, SAS will use 2 as the reference, and underlying is create a dummy variable underlying. Is not, you cannot see that, but actually create a dummy variable 0 and 1, and they use as 0 and 1 as 1.
So the function is the same.
Right, the function is the same, but it's actually underlyingly they're doing that.
Got you.
You don't know, you cannot see from that.
No, all right, now I got it. Thank you.
But as I said, they always treat to 0 and 1 for the no matter binary dummy or categorical.
All right.
I have a question regarding that, because actually what I did, it was like in the class statement, I specified sex. My reference in the sex as 1. So would that be okay?
So the sex is 0. So remind me, sex is 1 and 2, right?
Yes, it's 1, 2. I think 1 is for males and 2 for females. I'm not sure.
And then if you said 1 as a reference, so 1 would be the reference, right? The male would be the reference. But then SAS is actually underlying doing that thing, doing a dummy variable 0 and 1, and male will be 0, and female will be 1. You actually convert to the 0 and 1 variable that way.
Okay.
And then your interpretation will be comparing female to male, because male is the reference group.
That's exactly what I did.
Yeah, that's correct. That's correct.
Okay, thanks.
Wait, I have a question about what you just said. So if we put male, which is 1, as a reference group, they would be creating, SAS would be making females 0 automatically?
No. It will create a dummy variable, but you cannot see that dummy. They'll create a dummy with male equal to 0, female equal to 1, and use the 0 as a reference that way.
Okay, but then that wouldn't affect what we plug into the function.
They won't affect anything. But what you see here, what you see there is still you see the comparison between male and female and male, but you won't see 0 and 1, because if you plug 0 and 1, you can put into the model, right? Because you won't be able to plug in any other number to the model. So this is why SAS always first created 0 and 1 variable in that way. So only if you can plug in numbers. So otherwise, no way you can plug in the number that way, right?
Right.
Now plug in 1 and 2, because that will, if you plug 1 and 2, that will actually contaminate the result. It will not going to be the same result as you treat as a 0 and
Okay, and we actually had another question regarding that for the homework. So when some of us chose male as a reference group, others chose female as a reference group, and that was a bit of a problem when it came to the odds ratio estimates, because I believe that SAS is defaulted using males as the reference when it ran the odds ratio code.
So if 1 is male, 2 is female, right?
Mm-hmm.
So SAS, if you do not specify reference group, SAS will treat 2, which is female, as a reference. But if you put this ref equal to 1, SAS will use male as a reference.
Okay, it seemed like it was choosing 1 as a reference, not 2, from the code that we had.
I mean, that means you specify reference equal to 1.
Okay.
Without specifying that, SAS always treat the largest number, I mean by alpha, either largest number or largest letter, alphanumerically, as the reference group.
So how come we were getting a positive odds ratio? Wouldn't it be if it was choosing the negative, I mean the higher number as a reference, shouldn't we get a smaller odds ratio under 1?
Not necessarily. It depends on. Sometimes, like say, in some disease, male have a higher risk, and then you probably see a odds ratio greater than 1. And for certain disease, female have a higher risk, and then you will see odds ratio less than 1. It really depends, not necessarily.
Okay.
But for this, like say, in blood pressure exam, it's like say, usually male tend to have a higher blood pressure than female, just example. And then the odds ratio to have a higher expansion, higher hypertension. So usually male have a higher odds than female. So odds ratio will be greater than 0.
Okay. Can I share my screen with you for a second?
Sure. Let me check if share screen. Yeah, go ahead. I think you can do that.
Okay, so this here, I chose male as my reference group, and this is the output that I got. So my odds ratio for
Sorry, I cannot see the screen. Let me double check one more time. Maybe I need to stop sharing first.
Yeah, you need to stop sharing your screen. Yeah.
Okay.
You can also, where it says view options, you can also switch as well. There you go. It also, you have an option.
But I allow for multiple participants to share for now.
Yeah, you can actually see, you can actually choose when both of you are sharing between. You can actually choose.
Oh, okay. Let me see. Okay, but anyway, go ahead. So what's your?
This is my output. I chose males as my reference group, and this is the odds ratio that I got. Now, when I ran the unadjusted odds ratio, I got this output here. Now, mind you, when I did unadjusted odds ratio, I never specified a reference group. And from what it seems to me, and I want to be sure of that based on the values that I'm getting, it seems to me that it is using male as my reference group here. And that's
I mean, it's still a little bit hard to say. I need to look at your SAS code. It might be something else. I mean, or but this looks like this is male versus female because you have a odds ratio greater than 1.
Yeah, it's greater than 1. So I just want to make sure that we don't run into any discrepancy for the exam. Will you be specifying what to use as a reference group, and
no, it's up to you. As long as you do a correct interpretation, that's fine. Like say if you use a female as a reference group, that's okay. But your odds ratio will be 1 over that value. So it'll be 1 over 1.49, 1.5, something like that.
Yeah, I ran the program again using females as my reference group, and I got a 0.635 value for this year, and
which
0.4.
Right, which is by the way, which is 1 over that is equal to that number.
So 1 over, okay, makes sense. And I got an approximate value close to that for here too, which then reassured me that the program SAS was actually using males as my reference group by default and not females. So that was just an observation for anyone that's also choosing females as your reference group.
But hold on though, aren't they two different models with they're completely different, not completely different, but one has certain factors and the other one doesn't? Couldn't it be different? Couldn't they be very different and still be correct? Because it's not just, is it just specifically talking about the odds ratio for gender without taking into consideration the rest of the model?
In the multiple regression, it's hard to say because you have multiple, but in the simple regression, it's sure that just the reverse. Like say if you have also
but
to 20, but it's
for in the multiple, exactly. Couldn't that be very different than the simple in the fact that it has to take consideration for all the other variables?
Yes, it's possible. But your interpretation is different. As long as you do correct interpretation, it's okay.
Okay.
And also for the reference group is flexible, unless you have unless at your study design stage you really interested in certain comparison. Like say in the design stage you say we want to treat the male as the reference because we have a lot of data for male. So we want to use male as a reference, but want to compare female with male, and you can treat male. But I mean, if for other teachers, like say, if you use the secondary data, like data I gave you, it doesn't matter. You can use either one as reference, but if your interpretation is correct, I mean, that's fine.
All right.
Any other questions, Evelyn?
Oh, good. Thank you.
All right. So let me go back to share my screen. Go back to my screen. Okay. Yeah, and this is for the multiple logistic regressions. We have the net using the sector and also age as the predictor variable, but the mosquito net using and the sector are categorical variables, and age is the continuous variable. And the other thing is specify the event. So event, the variable do not have to be 1, 0, and 1. And if you have 1 and 2 in this example, so dung fever is 1 and 2, and 2 means no, 1 means yes. So this is the way you specify the event. So if you specify event equal to 1, SAS again will automatically quietly create a dummy variable 0 and 1. And actually 1 is the dung fever and 0 is no fever. And then again, there's not only one thing you need to worry about the reference. The other thing is you still need to make sure the specification of the outcome is also correct. Because if the outcome specification is not correct, you may still get a wrong estimate. You still can get a reverse the estimate of the odds ratio. So here, if we don't use event equal to 1, if we don't specify event equal to 1, SAS again will automatically use 2 as the event. They always use the largest number as the event. All right, and so in the result, we first have this fit statistics. So you just need to know. You don't have to really worry about what this means in statistics, but you just need to know AIC, SC, and -2 times the log likelihood. I also call this deviance. And these are all the model fit statistics. So we should use that to evaluate the prediction of the model itself. And the other thing you need to know is the value itself is not meaningful. It's meaningful only if for the comparison purpose. The value which is bigger for all of the three indicate is a better model. So that means you have to run multiple models and you compare the AIC or the SC or the negative 2 times of log likelihood between these models or among these models, and you can pick out the best model. But there's not meaningful to interpret the value itself. The interpretation for this value itself is not meaningful. We don't worry about that interpretation for this. And for the testing, there's a different test in the logistic regression. So the first test is the chi-square test for, we call the global null hypothesis test. This is similar to the in ANOVA or in linear regression we call OR test, just the OR F test. But here we don't use the F test because we use likelihood, just different models. No matter it's a different model, across all these different models, we all use a chi-square test because the likelihood ratio or the WAR test is similar to the likelihood ratio test, is a chi-square. We're going to a chi-square distribution. So this is kind of a chi-square test. So the entire global test is actually test the model as a whole. It tests all the degree of freedoms all together because you have 1 degree of freedom for age, 1 degree of freedom for net using, and 4 degree of freedom for the sector, geographic location, and therefore you have 6 degree of freedom for the whole model. So this is just the overall test for the entire model. And the null hypothesis is the entire model is significantly better than the null model. It's the model without predictor. And there are 3 different tests. All of the 3 tests are just tiny difference between the 3. Likelihood ratio, score, and WAR test. They were chi-square based tests. We see, I'm not going to go into too much details there. But in statistics, I can tell you they're very similar instead of the test statistic. And you can use actually either one to do the evaluation for the significance of the model as a whole. And the partial F test is just testing each parameter itself. Like for example, we can test the age effect. We can test the effect of net using. We can mosquito net. We can use you can test the effect of geographic location on the risk. So for example, testing the type 3 test for each degree of freedom, you have a WAR chi-square value, and you compare that chi-square value with the critical value 0.05 test level, and you can have the p-values. But here you can see age and geographic location are significant, but the mosquito net using is not statistically significant based on the p-values. And remember, here are all WAR tests for every single, for each effect that WAR test. But for the entire model, there are 3 tests: likelihood ratio, score, and WAR. But SAS only provide the WAR test for each factor. And also for each degree of freedom, we can have also the WAR test. And the first one is testing the entire, like say, the entire sector have 4 degree of freedom, you test together. But this one is to test every degree of freedom. So that means if you use sector number 5 as a reference, you were testing 1 compared with 5. 2 compared with 5, 3 compared with 5, and 4 compared with 5. So that's it for each degree of freedom test. And you can see even though the sector as a whole has a significant effect, not necessarily every single comparison have a significant effect. They only significant effect only comparing 1 with 5 and 3 with 5, but not 2 with 5, and 4 with y. And then after you have all these parameters, you can write down the specific model. Because the specific model is just a logit of that probability is equal to beta 0. Basically, it's simple for the model right up. It's just you plug in all the estimated parameters from beta 0, beta 1, beta 2, all the way to the last predictor, for the last coefficient of the predictor variables. All right, and parameter interpretation will be important. So for the parameter interpretation, I would more likely to use the odds ratio estimate, but you can still use this estimate. And remember, this estimate is a log of the odds ratio, but SAS just directly give you the odds ratio. So I would say it's better to use the odds ratio estimate, but you can also use this. There's nothing wrong. You use the log of odds ratio estimate as the interpretation. The only difference is you have to interpret this as the log of odds ratio, but you interpret this as the odds ratio. So for example, if you have an odds ratio 1.025 for age, but that's the odds of having down fever increased by 2.5%, which is this number minus 1 times 100%. So which means the odds of having down fever increase by 2.5% for every year increase in age. So that's for the continuous variable. But for the binary variable, which is mosquito net, using of the mosquito net, so you have to compare between two groups, because the not using mosquito net is the reference, and this value means the odds of having down fever increased by 39.6% with the absence of the mosquito net. And also for the factor of geographic location, which is the sector location. So you have to compare every single parameter with number 5, because number 5 is the reference. So for example, 1 versus 5, you have this about 0.11 odds ratio. So which means the odds of having down fever in sector 1 is 11% of the odds of sector 5. So here we're not comparing the increase of the odds, which is comparing the odds because it's less than 1. So this 0.11 or 11% is 11% of the odds of sector 5. It's not a reduction of 11%. But here that's the increase because you use this minus 1. And similarly, if you have odds ratio greater than 1, like sector 3 versus 5, so you can interpret that the odds of having down fever in sector 3 is 2.24 times of the factor. And also you can interpret as the increase is 2.24 minus 1 times 50%, which means it's about 124% increase in the odds if you live in sector number 3 compare with if you live in sector number 5. All right, so that's interpretation for the estimate in terms of odds ratios. All right, and also we can do this good enough fit test, even though it's called the lag fit option in SAS, but more people call this good enough fit. It's testing if the model or if putting this set of a predictor variable will have a good fit in the logistic regression model. So simply you just put in the model statement, you put a lack of fit option, and the test being used is called, we call this Hausman-Lammerschau good enough fit test. It's still, again, it's a chi-square test. But this is a testing this model with a reference model, the reference model which will have a good fit. So that's the idea of doing this a Hausman-Lammerschau test. And in this example, p-value is 0.69. So the null hypothesis is the model is adequate versus the not adequate for the alternative hypothesis. And therefore, your conclusion is this model is adequate. So remember, the null hypothesis is adequate. So that means you hope that you will not reject null hypothesis, because reject null hypothesis means this model will not have a good fit. Fail to reject null hypothesis will indicate this model is adequate or is have good enough fit, something like that. You need to know the adjusted odds ratio and adjusted odds ratio. So adjusted odds ratio is just in the model after you're adjusting for potential confounders. That's the corresponding odds ratio. So in this example, in the multiple regression, so what we got, the odds ratio is 1.0225. And the adjusted odds ratio is the odds ratio in the simple logistic regression model, and which is 1.25. It's 1.029. And you see there's a little difference. And again, here you can use this information to justify if the potential confounder is a real confounder variable. Because if the value here changed by more than 10%, you can conclude that the potential confounder being added is a real confounder. But one caveat I said in my video is this model, we're actually adding 2 more covariates. You should not use this as the basis for confounding evaluation. Because for confounding evaluation, you can only add 1 at a time to evaluate if that is a potential confounder. But here you're actually adding 2 other variables. I mean, this is a similar way, but you should not compare this with this in this example to evaluate if the 2 are confounders. All right. The confidence interval, again, you have to compare. You have to evaluate if the confidence interval of the odds ratio, including 1 as the benchmark, because odds ratio equal to 1 is equivalent to that, the beta 1 coefficient or the log of odds ratio equal to 0. So only if odds ratio equal to 1 or beta 1 equal to 0 indicate there's no effect of the independent variable or the exposure on the outcome. So the last topic is the evaluation of the which is the last part, evaluation of the predictive accuracy using the ROC curve. So the ROC curve can be generated only after you feed the model, and they actually use the predicted probability. So if you remember, that's the P, or the expectation of your Y, to create the ROC curve. So SAS get these things easy, because if you just have a predicted probability and you use the SAS code or use a prog logistic and you put the plus equal to ROC in the prog logistic statement, it will just automatically create that. But the thing is, the basis for creating the ROC curve is the estimated probability of having a disease, or the probability of the event. And they actually based on those events and the real observations of disease, 0 and 1, that's your outcome variable to create the ROC curve. This one thing I want you to know is how to interpret the area under the curve of the ROC curve. So this is the ROC curve for the model. So that's the sensitivity over specificity. And sensitivity is defined as the probability, the model specify this as a case, conditional on is a real case. So how you evaluate is a real case or not is from your observation of your outcome, because you already know the true disease status from your outcome, right? Because here the outcome, you know if you have a dengue fever or not. So that's from the truth. Or if you do not have the truth, because we need a gold standard. So gold standard is the standard you can specify is a real case or not. So like for testing of this COVID-19, so if you lack of a gold standard, it's very hard for you to evaluate if certain kids have high accuracy or not, because you do not have a real benchmark to say this is a case or not. So this is similar here. So because now you know the true case, you already know the infection status, you know if they're infected or not infected in this situation. And the model-based probability is just from feeding the model if you assign this as a case or not. So you can think of the model-based predictive value as a test result, and the 0 and 1 observation as a true result or a gold standard, either a gold standard or absolute truth. And then the goal is you evaluate the test result based on the logistical model can give you a high accuracy to evaluate them for accuracy for differentiate the case, which is not a control, which is non-case. So that's the goal. And I want you to know how to interpret this AUC. So usually AUC will be given after you run the ROC curve. Always you can see there's a row that area under the curve. So area under the curve is the same as AUC, which is short name. So this equal to 0.73 indicated predictive values from the logistic regression model. So basically predictive values predicted probability or risk from the logistic regression model on average will correctly classify 73.68% of the dengue fever cases. So that's the interpretation specifically in this example. But if you have a new example or like you have another study topic, it's basically considered as the percent of correct classification based on the logistic regression model. All right. So that's for the ROC curve. So the things I want you to know under this topic is that the relationship between the 2x2 table and the simple logistic regression model. So the take-home message is the odds ratio you calculated based on the 2x2 table is equivalent to the exponential of the beta 1 parameter in the simple logistic regression model. So only if in the simple logistic regression model you can have this relationship. The reason is the 2x2 table can only do n adjusted ones because you won't be able to factor out the to consider other factors in that simple 2x2 table. It can only do the marginal ones without considering the adjustment of the covariates. So the odds ratio calculated from the 2x2 table is equal to the exponential or the exponent of the beta 1 parameter from simple logistic regression model with the exposure variable as the only predictor. And you need to know the S shape. Also in the parameter interpretation. So it really depends on if your X is a binary variable versus X is a continuous variable. For the continuous variable, is basically odds ratio for 1 unit increase in that predictor variable. And for the binary variable, is basically the odds ratio comparing the other level with the reference level. And you need to know that interpretation on the exponential scale that's multiplicative is not the additive anymore. Even though you have a linear model on the right-hand side, you see is additive effects by all the predictor variables, but it's not interpreted that way. and also need to differentiate between odds ratio and log of odds ratios. So always keep in mind in the original parameter estimate table, we call the beta parameter table, that's the log of odds ratio. You cannot use that as the odds ratio. So if you want to use that, you have to manually doing the exponential function on that to give you the odds ratio, or you can use the SAS output for the odds ratio. Also, in order to test for confounder, you need to use that 10% rule. And also for testing the effect modification, you need to add interaction terms in the logistic regression model, and you need to evaluate that specific interaction terms in order for you to know if there's a significant interaction between the exposure and the potential effect modifier. And also testing the significant terms of that would be important. And the next thing I actually didn't include there is you need to know how to use the ROC curve to evaluate the predictive accuracy of the regression model, of the logistic regression model, or more precisely is to evaluate the predicted probability based on the logistic regression models. All right, I think that's all. Any questions on lecture 10, logistic regressions?
I had a question. Can you go up a couple slides? I'll tell you when to stop. Wait, that was...
This?
No, it has the equations written out. You were there. I think you wouldn't... Go back down, I think. Keep going down. Here. Okay. On the third line from the bottom where it says like probability of dengue equals 1 equals 0.035 divided by 1 plus 0.0335.
Yes.
Why is that a plus and not a minus?
Do you mean this one?
Yeah.
Oh, this is simply just a simple math, right? So if you convert this, I mean, just what if you call this x, right? Over minus x equal to this, and you can easily see this. This is a simple math by rearrange the rearrange all the parameters.
Algebra.
And this is called x-bit function. So if you look at here, so this is actually from this one right here, right? Because it's also equal to exponential to this whole thing divided by 1 plus. I don't know if there's a way I can show but I can write down on a simple piece of paper if you want to know that. But it's very simple math. Just if you convert this to this.
I have a paper written down if you want to use it with a justified equation.
Okay, Evelyn, you want to just send it to me?
I'll share it with you. Yeah.
Okay, thanks.
Yeah, this is just simple math. I hope I can show you. Is there a way I can show my... like a projector or something? Anyway, but I mean, if you just do this is a simple math.
All right, I think Evelyn will send it to me.
All right.
Yeah, I just got it actually from her. Thank you, Evelyn.
Problem.
Other questions? Or
I have a question, Dr. Hu. So I think I may have done this wrong. So when you said that if we use the word event, it's because the values are not 1 and 0, like the sex in our homework. So I used, sex reference number 2. So I'm thinking, so does that mean that everything is wrong because I should have used the word event equals 2?
Let me go there. So what you mean is do you mean for when you put the SAS code
Yeah, for when I do my SAS code, I do, you know, sex equals, sex parentheses ref equals, you know, quote to unquote and you know, and parentheses. But you have said also that if we have to use the word event equals when we don't use the 0 and 1.
No, the thing's different from the, so this part is for the predictor variables, right? And this part is for the outcome variables. The reason is the outcome is binary, is 0 and 1. And you may also have predictors, which is 0 and 1. So here, if you specify the event 0 and 1 reversely, is equivalent to you do a reverse specification of your binary predictor. So this is simply by saying a 2x2 table, right? So if you only have one predictor, which is outcome, one predictor, which is binary, and also your outcome is binary, this is going to be a 2x2 table. And you can have multiple ways to reverse that configuration of the 2x2 tables, right? You can put the event 1 as the first column, or you can put the event 0 as the first column. But the thing is, you'll end up with the odds ratio, which can be a reverse. So what I mean is, you not only need to correctly specify the reference group of your predictor variable, you also need to correctly specify the event in the outcome.
Yeah, so my, like the dengue event 1 is fine. It's just what I'm concerned about is the sex that I put reference, you know, ref. Should I change that to event? Would it change it?
No. So in the class statement is you specifying the so here in the class statement is generic. It's not just in the proc logistic, right?
Right.
It can be in proc GLM, it can be in proc REG, it can be any proc. So the rule to do that is called REF. There's no event to specify here.
Okay.
So event only in the model statement of proc logistic. This is not generic. This is not generic. This you cannot specify in proc reg. You only can specify the event in proc logistic. So this is only in the logistic regression.
So then my code is fine.
Your code is fine. And you can, but the other thing is, I think the take-home message for you is, you can use this standard, use this norm for all the class statement. It doesn't have to be in proc REG, proc logistic. It can be in proc REG and can be in proc GLM.
Okay. Okay, and then I have another question. When we have to interpret the adjusted odds ratio for sex in the homework, I use the point estimate, and when I do the 1 minus the point estimate, I get a negative number. Does that mean that instead of odds increasing, odds are decreasing, or how would I?
It cannot be a negative number.
Okay.
Do you use 1 minus the
point estimate?
Point estimate, it won't be able to.
Because my point estimate.
But you don't use 1 minus point estimate, right? Because
that's what I did. Because
your point estimate has to be compared with what you mean point estimate is the log of odds ratio, right? Just make sure.
So if you go to the, let me see.
Do you mean something like that?
So I'm looking at a table that's similar to the slide that you have the parameter there.
Here?
Yeah. So not specific. Yeah. This is the slide. You know, this is the output that I have on my SAS code. But for sex, I have 0.675. And on the slide, you have, you know, the point estimate minus 1 times 100 to get a percentage. So if I do that, I get a negative.
And if you do that, you can interpret like this way, right? Because this, as was said, if you have less than 1, you can see the odds of being in this sector 1 is 11% of that. So you don't have to use 1 minus this. So
okay.
usually if you have a greater than 1, you use this way.
Okay.
But you use less than 1, that means your odds is not being increased. Your odds is actually a reduction. You have a reduction in odds. So you can just say this 11% of that. Or if you can use 1 minus this. So 1 minus this means the percent of reduction in odds. But don't use this minus 1. Use 1 minus this. That's the reduction. But usually people do not interpret the reduction. They'll interpret the increase, percent of increase. If it's less than 1, you can simply just use this way.
Okay. Thank you.
Dr. Hu, how come when, for that same question that she's having, how come when you run the model using male as reference as opposed to female as reference, you get completely different values, even after you subtract from 1 for the male reference?
Mm-hmm.
So, for example,
as I said, the relationship is the 1 over the other one is this is equal to 1 over the other one, right? If you just simply switch around the reference group, so the point estimate the point estimate for odds ratio is 1 over the other one. So that way you can, if you it doesn't make sense you minus 1 that way, right? Because if you compare that way, it's 1. It is not a linear relationship. It is 1 over that is not a linear relationship. So you won't have that. But the link between them is 1 over the other one is the odds ratio for switching around the reference group. Or
yeah. So for example.
Yeah, go ahead.
Yes, for example, when I chose male as reference, I got for odds ratio 1.481, which technically is a 48% chance, right? That females,
right?
Yeah, exactly. However, when I did it the opposite way, I got 0.675. And how come these two numbers do not go with each other at all? Shouldn't they add up to, say, 100%?
They don't add up. As I said, the relationship is on exponential. The add up equal to 0 is on a log scale. So if you do log of that, you can see they up to 0. They sum up to 0. Log of 1 plus log of the other sum up to 0. The reason is the original point estimate beta is on a log scale. Now you already put on exponential scale, you lose that linear relationship. We won't sum up to 1 to 0. But the thing is, the product will be 1. So as I said, the odds ratio for that one times the odds ratio for the other one is equal to 1. So that's the relationship. Because now it's on exponential scale. So exponential scale, the product equal to 1 is equivalent to on the log scale, they sum up to 0. It is equivalent, it's mathematical equivalent.
Okay, got it.
All right, any other questions?
So just to clarify on that last question, you said that the odds ratios are basically reciprocals between if you're comparing one reference variable to another.
Mm-hmm. Right.
Okay.
If it's on a log scale, odds ratio, not on a log scale.
Okay.
Dr. Hu, I have another question, and this is related in the research paper.
Mm-hmm.
Do we actually need to extract some raw data from the sources that you provide us? And we need to run that data, we need to test the hypothesis that we're testing in SAS, so we cannot write out the conclusions or not?
That's right. That's what I hope you to do. But if you have not put into the plan, the draft, so go for the draft is just your plan, what you want to do. But I still want you to keep on the plan. Like say, if you haven't put on the plan, I don't want you to change the plan. You need to stick on the plan. But the things is right. I want you to have this. Like say the result, for example, if you run a model, you have this result. I want you to have the interpretation of the result and also the conclusion you get from there.
And because the thing is that I've been like having kind of trouble with that, because I went to the National Health Interview Survey, and they have, I don't know, so many questions, and for me it's been hard, like kind of interpreting the information that is in there. So
yeah, and then unfortunately you have to maybe change a little bit. But you know, when said you do that draft, I want you to make sure that the data is possible, or at least it's a possibility you can use this data to do this specific question. But if the data is not available, or you find later the data is not available, one way is you can check for the other years. I guess they have multiple years. You can check if there's data for other years.
Okay.
Or if not possible, you have to change a topic with when you have available data.
Okay. Yeah, I don't actually have like a specific topic. I've just been like kind of browsing like throughout the data sources to see what kind of information it's kind of easy for me to abstract from. So maybe that's why I've been like having kind of trouble. And something else, how can, once I find that data, how can I convert it into a table that SAS can read?
So SAS, not necessary to be a table, right? So you can, it depends on which open data source you use. So some open data source can give you CSV format, and some give you the SAS format. The YRBSS give you SAS format. Like I recommend, if you use the YRBSS, the use behavior study, they give you a SAS data set. And some give you CSV. It really depends on which study, which data you are using.
Okay. I'll look into that. Thank you.
I was gonna ask you really quick, do you have any good sources for data besides the sources you mentioned on the research paper assignment paper that you put on Canvas?
Yeah, I do, but the things that I said, I won't be able to give you the working in progress data. I can give you some published data. So this is our own database already been published. I can give you for that. But basically, because we already did some analysis, you basically just reproduce the result, right? It's not the you cannot have like a novel study, like a study have your own hypothesis. But for those data set we're working on, I cannot give you.
Hold on. So just I was looking for data, and just like the same issue as
Tatiana.
Yes.
Yeah. There's a ridiculous amount of variables in, for example, the surveys. So you really have to eliminate all of them one by one. That's not the only method, but that was the method I was using. But I was just curious if you had any other data sources besides those massive surveys where they're more smaller, they're smaller data sets, they're more specialized rather than such a wide.
Unfortunately, if you want to use open data set, it's usually a large data set. They're population studies. So the only thing, as I said, the only thing I can give you is if you do your own research, like my research, we do some, I think some research already published, I have a data set. So that's a possibility. But for the large open data sets, it's all like that.
Oh, okay.
So you have to dig into this, really narrow down to specific variable for that.
All right. Yeah.
Yeah.
And let's say that we find some data that may be available kind of easily. Can we just select, like, let's say we get, I don't know, we're testing for blood pressure in, I don't know, obese individuals. And then we have, and the data, we have the body mass index. And then we have, like, I don't know, over 1,000 subjects. Can we randomly select, like, I don't know, like 30 of those? Or
I would say not randomly select. I still want you to be research topic oriented. So you have to maybe choose a meaningful topic first, and then pick up the data and then see if the data can support this topic. And if you just randomly select, you may not have very meaningful study, right? So for example, if you can do some study, maybe you can see the relationship between blood pressure and family income, which may not be very meaningful, right? Could be meaningful, but you could, like, if you randomly choose it, you might find some very like goofy topic, you know, which may not make more sense scientifically.
Weird associations.
Yeah.
What I mean is that when I find the variables, like, it could be like body mass index in the case of blood pressure. So let's say that would be my variable, like my predictor variable. So I'll be saying, okay, people who have like higher body index, high mass of body index, it's more likely to be hypertense or have higher levels of blood pressure. And then I found a data source, and then I find data, I don't know, on over 1,000 individuals for the predictor variable body mass index. Can I just get 30 data sets or 30, I don't know,
30 observations.
30 observations exactly of those 1,000 plus to conduct the study, or to at least
you mean
base my project?
Select?
Yeah, randomly select of the ones that have, that I have body mass index information on, since that's my predictor variable.
Yeah, so I think the only benefit to do that is your computational load is smaller than but if you have a large sample, always doing a large sample analysis is better.
Should be easy.
Because I'm using small data set, it's just for demonstration purpose. It won't be a big difference if you're using SAS. So using SAS to run a sample size 30 may not have a much difference like you run sample size equal to 1,000 or 10,000. Unless you have a huge number of observations.
But wouldn't you like us to check for outliers for those observations?
It depends. So for the large data set, as you see in my lecture 6, right? Because you can just like automatically rank the data, and you see what's the 5%, 10%, and you can just like process them like in a batch. So you can automatically just tease out, like you remove the higher 5%, 10%, but you don't have to look at them one by one. So that's the way for dealing with the outliers.
Is there, let me ask you real quick, is there must be some criteria on which outliers you can select. Is it just the ones that you went over in the lecture? Because you're saying like cutting out 5%.
Right.
And
10%. You're right. There's multiple way. You're right. It depends. But I mean, just for simplicity, if you not want to do a research, like say, sometimes we tease out outlier because we have some scientific reason for that. But for this kind of secondary data, because you didn't collect the data, it doesn't make sense. You have some scientific reason for doing that. So usually, if you just for that purpose, you can just do.
Yeah, I got you.
And to remove or something like that.
Okay. All right, and also the last. So you really want the data to be meaningful. There should be some.
It would be better, I would say.
Because that doesn't always work out that way, you know.
Yeah, I know. But I mean, if you cannot get right, the data perfectly makes sense. But you can at least do something which makes sense. Not,
meaningful. Yeah, I got.
Not completely, you know. Yeah, not completely
yes.
off.
You're testing something that has reason to possibly be true.
Yeah, will be considered as a research topic, or at least you can. I mean, I want to publish that, but maybe a publishable topic.
Yeah, I got you.
I don't know if you, but it's not like that straight. Like you choose a PICO question, right? If you learn the evidence medicine, there's a PICO question. It's not like that. You don't have to do it like that, but just at least a topic which can make sense, at least scientifically makes sense.
Yeah, got it. All right.
Dr. Hu, if you want, just stop recording because I feel like it's going to get eternal for you to wait.
Okay, right. Yeah, just forget. Yeah, it's so long for me to convert that to the MP4 data. Let me see how to.